Okay, so in this video, we will discuss systems of linear equations, or simply put, linear systems. All this is trying to solve several linear equations simultaneously. Consider first a very simple example with two variables, x and y, and two equations. So suppose we ask to solve this equation, so 2x plus 5y equals 4, but not just this equation alone, but at the same time, simultaneously, the other equation, 3x plus 7y equals negative 6. So when you ask to find a solution to this so-called system of linear equations, you're asking to find a value of x and a value of y that satisfies simultaneously the first and the second equation. Well, let's see how we could do this. Let's try to isolate x as a function of y from the second equation. So this will give us that 3x is negative 7y, negative 6. Dividing by 3 on both sides, x will be negative 7 over 3, y negative 2. So now we have that the second equation is equivalent to x being negative 7 over 3y minus 2. We can now make a substitution. We can replace in the first equation x by this function of y, which will now give us a unique equation as a function of one variable. This will allow us to solve for y. So we have 2 times x, negative 7 over 3y, negative 2, plus 5y equals 4. From the second equation, one equation, one variable, we should be able to solve for y quite easily. Let's multiply by 2, so we'll get negative 14 over 3y, negative 4, plus 5y equals 4. Add 4 on both sides, so you'll get 4 plus 4, which is 8. And here, well, you want this to be out of 3, so you have negative 14 over 3y. 5 is 15 over 3y. So all you're left is with 15 minus 14 is 1, so it's y over 3 is equal to 8. Multiply by 3, and so y is 24. So we have found a unique value for y. By solving for x in the second equation as a function of y, replacing in the first equation, we found that y must be 24. Well, we can easily now get the value of x by replacing y in here by 24. So what do we get? Negative 7 over 3 times 24, negative 2. 24 over 3 is 8. 8 times 7 is 56, so negative 56, negative 2 gives us negative 58. And so we have now our unique solution. The only way to find a value of x and y that satisfy both the first and the second equation is for x to be negative 58 and for y to be positive 24. So here we have a unique solution. Let us verify that we haven't made a mistake in our calculations. Let us substitute back in the original linear system and see that both equations are indeed satisfied. So we have 2 times x, which is negative 58, plus 5 times y, which is 24. Let's compute and see that we get positive 4. 2 times 50 is 100. 2 times 8 is 16, so that's minus 116. Plus 5 times 20, 100, plus 5 times 4, 20. That's 120. And 120 minus 116 is obviously positive 4. Check. The solution satisfies the first equation. Let's look at the second equation now. 3 times x, 3 times negative 58, plus 7 times y, which is 24, equals, well, 3 times 50 is 150. 3 times 8 is 24, that's minus 174, plus 7 times 20 is 140, 7 times 4 is 28, so that's plus 168, and negative 174 plus 168 obviously is negative 6. So indeed, x equals negative 58 and y equals 24 is our unique solution to this linear system of equations. Two equations and two variables. It's clear if we had eliminated this equation and only solved the first one, we would have obtained an infinite number of solutions. But because we have to satisfy both equations simultaneously, we only get a unique solution. Okay, well that wasn't too hard. What if we had, say, 3 equations and 3 variables? How would this play out? Suppose we had the following linear system. So 2x plus 7y minus 16z equals 11. Negative x, negative 3y plus 5z equals negative 8. And 3x plus 10y minus 20z equals 21. So now we have a linear system and 3 equations, 3 variables, x, y, z. So by asking to solve this linear system, we are asking to find all values of x, y, and z that will simultaneously satisfy these 3 equations. Well, if you think about it, we could do the same thing that we did in the previous problem, right? We solved for x as a function of y, then we solved back into the first equation, and then we were able to solve for y, then going backwards, solving for x. Well, we could play the same game here, but this will be slightly more unpleasant, right? We would have to say solve for x here as a function of y and z, then replace x as a function of y and z, then we'll have 2 equations and 2 variables. We could then solve for y as a function of z here, then replace y as a function of z, then we would have 1 equation and 1 variable z. We would then have the value of z. Going backwards, we'd figure out the value of y. Going backwards, we'd figure out the value of x. And we would find a unique solution. But this is quite unpleasant. I will leave it up to you to actually do it. So solve for x as a function of y and z, substitute, solve for y as a function of z, substitute, solve for z, then go back, solve for y, then go back, solve for x. And if you do so, you will find a unique solution. And x must be negative 3, y must be 7, and z must be positive 2. Not difficult, just a bit on the long side. Let's at least verify that this is our unique solution to this linear system. So 2 times x, 2 times negative 3, negative 6, plus 7 times 7, 49, minus 16 times 2, minus 32, equals, well, let's see, 49 minus 6 is 43, minus 32 is indeed 11. Check. Second equation, negative x is positive 3, negative 3 times 7, negative 21, plus 5 times z plus 10, equals negative 21 plus 3, negative 18, plus 8, negative 8. So far so good. Finally, third equation, 3 times x, negative 9, plus 10 times 7 plus 70, minus 20 times 2 minus 40, 70 minus 40 is 30, minus 9 is 21. So indeed, x equals negative 3, y equals 7, z equals 2 is a solution to the linear system. And it is a unique solution. You could ask, well, what happens if we say drop third equation? And now we only have two equations and three variables. And what you would find in this case would be an infinite number of solutions. Z would be a free variable, it would be a parameter. And then x and y would be functions of the parameter that we choose for z. But now you could say, well, what if we considered, say, a linear system in four variables and four equations? Could we do the same thing? The answer is yes. But if you think that this was bad with three equations, three variables, it will be a lot worse with four variables, four equations. What if you had five equations, five variables? This would be a ton of work. Way too many calculations and way too much writing. So our natural question now is, okay, can we do better when we try to solve these linear systems? And we can do better in two ways. First, if we use good notation, we can save ourselves a ton of writing. Second, if we figure out a clever way of simplifying the systems, then we can save ourselves also a ton of calculations. And this will be the topic of our next few videos. How do we systematically and most effectively solve any linear system, sorry.